All right, let's try this one. Let's see. How do you calculate for the case of a dipole? If you had a dipole and you wanted to find potential difference VD minus VC, what should you do in terms of summing up the potential differences? Would you use one path segment, two path segments, three path segments, or would you have to do an integral in this case? Okay, most of us are saying we have to do an integral. Some people are saying we have to use two path segments. Well, the path is from where to where? It starts at C and it goes to D, right? So we're going from here to here. Now, maybe the question wasn't as clear as it could have been, but in the previous, let's scroll back to a previous question. How many path segments did we use in this case? We used 3, right? Along each part of that path, the field was uniform, but it differed from one segment to the other. But in the case of a dipole, from C to D, what's happening to the electric field? It's changing, right? It's changing in magnitude. How is it changing in magnitude? What's the distance dependence? R cubed, 1 over the distance cubed, right? So we have another situation where you'd have to do an integral, right? Just like for the point charge, where the field is varying across the entire length of the path. You again make the, think about it as breaking it up into really, really small pieces of the path and just adding all those pieces together. That's what we mean by doing an integral. Okay. So the point is, anytime you have a non-uniform field along a region where it's dependent on distance, it's varying with distance, you need to actually do the integral in order to calculate the potential difference. Okay? And you'll have a couple questions in a web assignment that's coming up where you would have to do some things like this. Okay. All right, we have, let's see, 5 minutes left. I want to set up an example that we will finish up next time. Well, we already talked about this, right? We would have to do a potential difference of 3 path segments for this case. And this is a case where we have a capacitor with a metal slab in between the 2 plates. Let's start off by just looking at a capacitor. 2 charge plates. One has a positive charge. One has a negative charge. Charges are equal but opposite, so that's plus Q and this is minus Q. Inside the electric field is uniform, right? That's the result for the electric field inside a capacitor, where the size of the plates is much larger than the distance s between them. So we have a region of mostly uniform field. And let's say that, let's call this point A on one plate, point B on the other plate, across that distance s. Let's say VB minus VA is VB minus VA, so we're going along a path that's in the direction of the electric field. It should be negative, and let's say it turns out to be negative 1,000 volts. Okay. So let's say I also know the distance between the plates. We'll say that S is equal to, let's make it 2 millimeters, or 2 times 10 to the minus 3 meters. So if I know the distance S and I know the potential difference, I can say that the electric field, well, let's do it this way. VB minus VA is going to be the negative of the magnitude of that electric field times the magnitude of that distance times the cosine of 0, right? Because we're going in the direction of the path. Cosine of 0 is 1. So that's the result. So I can solve for the magnitude of the electric field by saying it's negative 1,000 volts, and the signs will cancel, so that'll give me positive times 2 times 10 to the minus 3 meters. So the magnitude of the field inside the capacitor is going to be 5 times 10 to the 5th volts per meter. Okay? So that's the result when we just have air in between here. There's nothing in between except just air. And then we drop a metal slab in between the two plates of the capacitor. Okay? So we'll leave you well, where is this question? I thought it was here. Let's go back to here. Last question. Real quick. What do you think is going to happen to the electric field in this region and in this region when I drop the metal slab in between? We have a vote all the way across the board. Some say same as originally, some say less than originally, some say greater than originally. So think about it. We'll talk about it next.